Hi, my name is Corinna Wester, and this is my lab video for Lab 4, Circuits and Capacitors. So the skills and purpose of this lab is to create and modify circuits to start working with bulbs, emitters, and capacitors. And we're learning how to use the loop rule, which has to do with energy conservation, and use current conservation. And we're going to use both of these to predict and model circuit behaviors. So the first step was just to get a general visualization of a simple circuit. So using our online circuit kit, we modeled the circuit with two 1.5 volt batteries, two resistors, 147 ohms and 100 ohms, and two emitters. Like I said, this just modeled a simple circuit, and the emitters gave us a visualization of the strength of the current. Next, we removed one of the emitters and replaced it with a voltmeter. Now, because of the loop rule, we know that the sum of all the potential differences has to equal 0. And we know that the batteries are each 1.5 volts each, which equals 3. And because it's an open circuit and there's no current flowing through the wires, we know that the potential difference across this break must equal the EMF, which it does. And if we closed the circuit with a wire, we kept the voltmeter in the same position, we would see that it was 0 volts across this spot, because at this point, with a current flowing through the wires, now our only pieces we need to be worried about are the batteries and the two resistors. So there would be no potential difference across that piece of wire. So this was just a model of the potential versus position of the circuit. So we know it started out as 0, and as we go through the batteries, it goes up linearly, and then it levels off until it gets to the first resistor. And the first resistor, if you calculated the potential, it would be about -1, and then it's going to be constant until the second resistor, and that's going to take it to 0, because in this ideal circuit, the ammeter has 0 resistance. Next, we modeled a simple parallel circuit, and we put one of the ammeters in parallel with the 100 ohm resistor. And as you can see here, the end amperage is the same as the amperage flowing through the right side of the parallel, and that's because when a parallel circuit is present, the current will take the path of least resistance. Next, we modeled an RC circuit using a 9 volt battery, a 10 ohm bulb, and a 200 millifarad capacitor. I observed how long the capacitor took to charge and then discharge fully, and also observed what was happening with the current. And then we repeated these same steps, replacing the 10 ohm bulb with a 20 ohm bulb to see the difference. So here's just the visualization of what happened with the 10 ohm bulb. For the capacitor to fully charge, it took about 5.5 seconds, and to fully discharge, it took about that same amount. And also, you can't see it from these still images, but as when the capacitor was fully discharged and we turned it on, then we saw that the bulb glowed brightly at first and then slowly dimmed. And then the same thing when we disconnected the bulb and connected the fully charged capacitor to the light bulb, it was the same thing. It started out very strong, but as the capacitor discharged, the light bulb dimmed. Same thing for the 20 ohm bulb. This just shows that the greater the resistance, the longer it takes for the capacitor to charge and discharge. So now we're modeling an RC circuit with math. And so we created a new circuit with a 9 volt battery, a 200 millifarad capacitor, a 30 ohm bulb, and a voltmeter. And what happened was we wanted to observe the voltage difference across the capacitor as time increased. So you can see here, we have our circuit and the voltmeter placed across the capacitor. And as you can see on the Excel spreadsheet right here, I went in 2-second increments up to 20 seconds. And we see we have a linear decrease of time versus voltage. And from this, we know that our slope of this line should equal -1 over our RC value. So our RC value computationally is 5.99988. And we know that RC, the resistance for this was 30 ohms, and the capacitor was 200 millifarads, which is 0.2 farads. And when we multiply those together, we get 6. So as you can see, these are very similar numbers. So we did it right. So our final questions in conclusion. What if we were doing this lab in real life and used an actual ammeter instead of an ideal stimulated ammeter? What's different about a real ammeter and how would it have affected the circuits? Well, in our ideal ammeters, they had zero resistance, so this would have changed using a real ammeter. It likely would have some internal resistance, so you would have to take that into account with your circuits and calculations. And if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, what would happen? And how would our ideal model differ from a virtual model, or how would an ideal model be different than a non-ideal model? Well, ideally, the battery would charge the capacitor instantaneously, but in reality, this wouldn't happen because batteries do have some internal resistance. Also, in real life, it could just short the battery out. So in conclusion, this lab used simple circuits, parallel circuits, and RC circuits to model and predict ideal circuit behavior. Thanks for watching.